Hi, I'm Dr. William Yang, and this is an introduction to open science, why open science should matter to every researcher today. This talk was prepared for the University of Missouri Reproducibility Journal Club recently. A bit about myself. I got my PhD from the University of Sydney, and I was supervised by Alex Holcomb and Patrick Goodborn. And one of the first projects that they had me do as I was starting my research training was to do a replication. So on the slide here, I have a comic by xkcd.com. At the time, I had been taught in high school science that scientists tend to repeat the experiment to ensure the same thing happens. You can see in this comic in the bottom left, after a shock has occurred, a normal person may react and not try again, whereas a scientist may try and recreate the experiment. So one of my first projects was in fact a replication project of a repetition blindness experiment. And I simply helped out with the data collection. And at the time, I thought replication was commonplace in science, and I thought this was a normal thing to do. To my shock, the replication project that I helped out with was actually part of the Reproducibility Project psychology, which I'll mention later in this talk. It turns out that replication isn't as commonplace as I believed it to be. And I was also shocked to learn that many graduate students in their research training are potentially unaware of the current replication crisis going on. So here in this talk, I'm going to try and do a few things. I'm going to try and lay out the events that led to the reproducibility crisis, try and explain what the extent of this crisis is, and some reasons for researchers to engage in open science and perhaps some ways to do so. So firstly, what is the reproducibility crisis? Well, it's the recent and collective concern that many scientific studies have not replicated or are difficult to replicate. I want to highlight here that replication concerns have existed throughout the history of science, except this particular moment in science, this reproducibility crisis as it has been termed, has been extremely impactful and seems to be the wave that will really change how science is being done. A combination of a lot of media attention and the internet and the large call to action from the events that I'm about to explain will show why this reproducibility crisis has come about. Here, I'm going to start off with my field of expertise, which is in psychology, but note that the reproducibility crisis is relevant to many different scientific disciplines, and hopefully the concepts generalize to your research field. So firstly, in psychology, the first event that sort of triggered the call to action by scientists in the reproducibility crisis sort of starts around the time of Darrell Bem in 2011 publishing experimental evidence for precognition. In 2011, this solo paper named Feeling the Future, Darrell Bem, who at the time was a well-known and respected social psychologist and professor, published a paper claiming positive evidence for precognition and premonition. So for those of you who are unfamiliar, precognition and premonition is the ability to predict the future, to know what's coming. In this paper, it had 9 experiments and 1,000 participants, and seemingly standard statistical analyses such as t-tests and ANOVA. It was also published in the Journal of Personality and Social Psychology, a highly prestigious journal, and this was after peer review. This paper received widespread criticism and a lot of attention from the scientific community, mostly criticizing these results. And it was a shock to many that such an established researcher could find evidence for an impossible hypothesis. Not mentioned on this slide is Wagemakers and others doing a Bayesian analysis of the data and finding that there was no evidence for a significant effect or substantial effect. And here I've also highlighted on the slide a pre-registered replication which failed to find any of the reported effects in 3 attempts. This was by Ritchie, Wiseman, and French. What's also shocking about this pre-registered replication was that it was rejected at 4 journals. It was rejected at the Journal of Personality and Social Psychology, where the original BEM 2011 paper was published. It was also rejected at the British Journal of Psychology, supposedly where Daryl Bem had been one of the reviewers. So this occurred, and almost coincidentally, Simmons, Nelson, and Simonson in 2011 published a paper showing how selectively reporting data and analyses may produce false positives. So Simmons and others in this paper actually did some data collection where they played to their subjects 2 songs, When I'm 64 by the Beatles and Kalimba. Then they also asked their participants' age and other demographics. And then after statistical analysis, they found evidence that listening to music can cause people to become younger. So that is, an ANCOVA revealed people were nearly a year and a half younger after listening to When I'm 64 rather than to Kalimba. And you can see the p-value for that statistical test was 0.04, less than 0.05. So therefore significant. Clearly becoming younger is impossible, so this is an example of a false positive. However, this influential paper brought to light certain research practices can produce these false positives, actually inflate the likelihood of obtaining a false positive. On the table on the right, here are 4 of those practices where researchers have a decision that they can make about the type of statistical analysis. For example, situation A, where they collect 2 dependent variables and perhaps selecting one of the variables or only reporting one of the variables that are significant, or combination of the 2. Situation B, where you add 10 more observations per cell after looking at the data, perhaps to check if it was significant, the p-value was significant or not. Situation C, where you add in a covariate and you control for gender or an interaction of gender with treatment, for example. Or situation D, where you include or choose not to include one of 3 conditions that you may have tested in your experiment. So notably, we select an alpha of 0.05 and we are claiming that we're okay with a false positive rate of 0.05, but these decisions end up inflating the false positive rate beyond that 5%. So for example, you can see there in the table, using a combination of all the 4 questionable research practices, as they are now termed, can inflate the likelihood of a false positive rate up to 60.7% at a p-value of 0.05. That's beyond 50%. It's more likely you are going to obtain a false positive in this case. So this analysis showed to psychologists that there is an issue of researcher degrees of freedom, or analytical flexibility, where researchers in their decisions to make an statistical analysis, or within a statistical analysis, can insert their bias and therefore inflate the false positives. And it just so happened that it appears that these research practices appear in Daryl Bem 2011, where, for example, there are some suspicious sample sizes. Some experiments had 50 subjects, some experiments had 100 subjects, some experiments seem to be a combination of those subjects together. So there were unclear designs up front. Some participants reportedly experienced a certain condition while others didn't, but those data were combined together. There was use of one-tailed tests, which are usually reserved for certain situations where the effects can be assumed to be in a certain direction, and using a one-tailed test gives you more statistical power, but perhaps is an improper statistical decision. And also using non-standard measures that had been constructed post hoc, looking at the dependent variables and combining them and not having them validated beforehand to look at these effects. So it seemed like we had Daryl Bem produce a false positive, which was shocking, and Simmons and others showing how that false positive may have come about. Following that, John Lowenstein and Prelek in 2012 surveyed psychological researchers about their practices, including an incentive for truth-telling. So these were their results. On the x-axis, you have different questionable research practices, and on the y-axis, you have the percentage of researchers that admitted to conducting these questionable research practices in the dark gray bar. You can see there failing to report all dependent measures, for example, only reporting the dependent measures that showed significant results. 78% people surveyed admitted to doing that. 72% admitted to collecting more data after seeing whether results were significant. So this is p-hacking, where you check if the results are significant and you add data in the hopes that your p-value may drop below less than 0.05 with the addition of more data. 67% selectively report studies that worked, i.e. only report the experiments that showed a significant result. 62% exclude data after looking at the impact of doing so. For example, perhaps excluding an outlier when that may increase the significance or increase the effect size of the result. These are only self-admission rates. From those self-admission rates, John Lowenstein and Prelek estimate the prevalence of these questionable research practices in the literature to be close to 100%, as you can see here by the lighter gray bar. So these three papers together and others that I haven't included here, these events led researchers to realize, oh, there is a potential preponderance of false positives circulating in the literature because of these potential questionable research practices being included that insert researcher bias into the results. And potentially psychological researchers are unaware that this is questionable. These papers sort of sparked efforts to try and then replicate results to see which ones were reliable and true. So here I've listed 4 of the main projects that were large-scale replication efforts in response to these potential issues. The most notable one is the Reproducibility Project Psychology, which I mentioned earlier on at the start of this talk. Here, only 39% of the 100 studies that had been previously published in high-ranking psychology journals were replicated. Of the 97 of those that had positive significant findings, only 36 of them replicated. In other large-scale replication efforts, now termed mini-labs, 14 of 28, which was 50%, of the psychology findings were replicated with huge sample sizes. And in mini-labs 3, which was in academic samples across time, only 3 of the 10 psychology findings replicated across multiple participant pools. And in the prestigious journals Nature and Science, only 13 of the 21 social science experiments that had been published there between 2010 and 2015 replicated. This is overall a poor strike rate for effects that are replicating in psychology. So in combination, some researchers started to believe that and have proposed that most published research findings may be false. This is a provocative and influential paper by John Ioannidis. In this paper is influential for many reasons, and one of which is statistical power and the simulations of what that is. So firstly, let me explain what statistical power is. Statistical power is the probability of rejecting the null given that there is a true effect. So the probability of a significant result given a true effect. You can also think of it as the inverse probability of making a type 2 error, so the probability of not missing an effect or not making a false negative. I just want to point out that statistical power is not the positive predictive value. The positive predictive value is the probability of a true effect given a significant result. And this is something that we want to try and maximize and optimize in scientific research. So statistical power doesn't necessarily equal the probability of a true effect given a significant result. However, what is the relationship between statistical power and the positive predictive value? So here, these are the results of simulations run by Ioannidis previously, and here I've taken the figure from Button and others. On the y-axis is this post-predictive value, which is the post-study probability here. On the x-axis is the pre-study odds. The pre-study odds is the probability of a true effect. And many think that this is a low value because out of the many potential hypotheses in the world, what is the likelihood of one of those being true? So because it's one of many, these pre-study odds is likely to be very low. However, we have no way of knowing what the true value is in science. So, however, here the three lines demonstrate the relationship between statistical power and post-study probability, or this positive predictive value. At 80% power, which you might have heard of as the convention for statistical power, if we're using 50% as a benchmark to figure out whether most published findings are true or not, you can see in the 80% power condition, this curve is very steep and reaches an acceptable positive predictive value quite quickly. We are not reliant on what the probability of a true effect is. At 30%, you can see it plateaus much later and at a lower level. So it's much more difficult to get to this 50% benchmark for post-study probability. And at 10%, it's even dire, even worse. You can see at the most optimal scenario at a really high pre-study odds, it's barely reaching above 50%, closer to 60% positive predictive value. So, given this relationship between statistical power and the positive predictive value, what has statistical power been in science previously? Well, the news is not good there either. Smaldino and McElreath, in a review of the literature in the past 60 years, estimate statistical power to be approximately 24%. Button and others in neuroscience disciplines suggest that the median statistical power is approximately 8 to 31% across the various subdisciplines in neuroscience, pointing out that neuroscience is affected by very small sample sizes and therefore very low statistical power. Specifically in psychological research, Stanley, Carter, and Duoliagos in 2018 suggests that the median statistical power is 36%, and for median-sized effects, which are the majority of the effects in psychology and cognitive neuroscience, the statistical power has been 44%. So the estimates of statistical power across literature, across science, and also within psychology have been fairly low and nowhere near the purported 80% convention that we should be reaching to ensure positive predictive values are high. So this may contribute to a high prevalence of false positives in the literature. And that's not the only bad news I have. We are also influenced by publication bias. So publication bias is the belief that positive findings, usually those with larger effects, are more likely to be published compared to null findings. And also the belief that novel findings are more likely to be published than replications. So this can contribute to the number of positive results in the literature and a lack of null results to correct what is happening in the literature, to correct those false positives. And in addition to the publication bias, we have a system that currently has a lot of paywalls, so many paywalls. So it's incredibly difficult to access research in the first place and then to do a direct replication of those results to see if the effects that are reported are reliable or rigorous or not. So all of these together are threats to reproducible science. So here, this is a figure taken from Munafo and others' manifesto for reproducible science. I've gone through a few of these here, but I'll start from the top right of this circle, where when we generate and specify a hypothesis, we may fail to control for researcher bias. When we design a study, we may have low statistical power. When we conduct study and collect data, we may have poor quality control and measurements, something I haven't mentioned up until now. When we analyze the data, test hypotheses, and interpret the results, we may introduce questionable research practices and introduce researcher bias, so that we p-hack and produce the likelihood of false positives increases. We have that arrow across called harking. For those of you who are unfamiliar, that's known as hypothesis after results known. So you may look at the results post hoc and decide that you knew all along that the effect was in a specific direction and choose to use a one-tailed t-test instead of a two-tailed t-test. So therefore you get a significant effect, for example. And lastly, the publication bias that I briefly mentioned. And you can see that this figure shows that this could be circular and continually occur as threats to reproducible science and to perpetuate false positives in the literature. So in combination, all of this sort of has brought rise to the reproducibility crisis. So psychology researchers have realized that decisions made on statistical analysis can introduce bias and increase the likelihood of false positives, and perhaps without any awareness, with perhaps intentional, but also psychology researchers may be unaware that they are doing this. Large-scale replication efforts have failed to replicate the majority of published findings, and when they have replicated, effects tend to be smaller than actually reported. And this is problematic when we try and apply those effects in other scenarios. Estimates of statistical power have been considerably low in psychology and across science, which suggests a high prevalence of false positives. And all of these factors in combination and all these realizations happening in a short period of time has led to widespread attention from scientific researchers and media attention terming the reproducibility crisis. However, bringing these issues to light has also brought about a response or a call to action from researchers. I love this tweet from James Heathers, who is a scientist himself and host of the Everything Hurts podcast, which I recommend. In this great tweet, he says, "Science is self-correcting, sure, when we correct it, not because of magical progress." So, in a response to these issues being brought to light, scientists have worked to figure out what's going on and have pushed for methodological reform. So, in other words, rather than call this a reproducibility crisis, and rather than being all doom and gloom like it might appear in the first half of this talk, you may look at this as some sort of credibility revolution, to borrow the words of Samin Bazir. There has been a response by researchers to try and correct what is going on in science. So this has culminated in something called the open science movement. Here I'm using the term open science movement to encapsulate everything about this as a completely inclusive term. Here, Cruel and others defined it as an umbrella term used to refer to the concepts of openness, transparency, rigor, reproducibility, replicability, and accumulation of knowledge, which are considered fundamental features of science. So here I'm sort of referring to the wide scope of the open science and the methodological reform that has happened as a result of the reproducibility crisis and the call to action. And this movement is rapidly growing and evolving and is changing and how science is being done, and I think improving how science is being done. What does the open science movement actually entail? Some of it includes things like open sharing of experimental code, data, and research materials, focusing on doing more replications and reanalysis, using preprints and open access publishing venues, as well as pre-registration and registered reports, and furthermore that I haven't encapsulated in this slide here. So why do open science? Why take on those open research principles? This is a figure that I just pulled off Wikipedia from the University of Cape Town. I will go through it to explain why some reasons to do open science. Starting from the top left with efficiency, that more research can be produced from the same data. I have a personal anecdote about this. My most recent paper involves a reanalysis of two previously collected data sets. Those data sets were collected for completely different reasons, but those two data sets are completely openly and available on the Open Science Framework, and they had qualities. In my case, they were large, had many subjects, and were EEG data, which allowed me to estimate the statistical power of a commonly used measure in my field using a subsampling analysis. So I could use that previously collected data set to answer a completely different question and produce more research. So it allows for efficiency, it allows for more research from the same data. On the top right, which I think is a critical point to doing open science, it allows for greater evaluation and scrutiny. So it allows reviewers to check whether someone's data and analyses are reproducible, and also improves their feedback, which I'll go into further detail later. So rather than relying on the manuscript, which can be just an anecdote, equivalent to an anecdote, and removing the sort of trust exercise that is peer review of a polished manuscript, reviewers can themselves go to a data set and check whether the quality of data is good or whether the experimental code is good, and whether the manuscript reports the actual effects that it is claiming to. So it allows greater criticism and greater evaluation and scrutiny, which ensures the rigor and reliability of the research. Other reasons include innovation, reducing delays in the reuse of scientific research. I want to point out that given the global COVID-19 pandemic, open science principles has allowed researchers to communicate and develop a vaccine faster than any vaccine has been developed in the history of the world. So it allows quicker and efficient innovation towards scientific progress. It on the right-hand side provides economic benefits. It plays a key role in today's knowledge economies. I will also add that it brings about, it levels the playing field, because if no longer is the knowledge specialized to a specific group to produce that knowledge economy, if that knowledge is openly accessible to everyone, anyone can access and produce that knowledge economy, specifically those who are often underrepresented or marginalized will have the same access and can therefore benefit from the knowledge. And similarly, in the bottom left, it allows us to have public disclosure and engagement. As a psychology researcher, I'm sure others like myself are concerned about the age of misinformation and how the public make scientific inferences themselves. Perhaps having open access to manuscripts and preprints, which I'll talk about later, allows them to make better inferences about the scientific questions that they have. And it promotes engagement between scientists and the public, and can help scientific communication and also promote citizen science. And last but not least, the global benefits of open science. It promotes collaborative efforts, which have been somewhat lacking in the pursuit of science, where science tends to have been stereotyped as an individualistic pursuit for the truth, whereas collaboration and community are very important impacts and efforts as we try and improve science and try and improve the impact of science. Here, that spiel and this figure are global reasons to do open science, but there are also personal reasons why you may want to do open science. I have them listed here. So some personal reasons to do open science: it may improve the quality and reliability of your own scientific research. Here I'm going to use, for example, pre-registrations. So pre-registrations involve answering a survey about your experiments, usually hosted by Open Science Framework or aspredicted.org or clinicaltrials.gov, where you answer questions about your experimental design, your hypotheses, your sample size and any power analyses that have come with that to justify a sample size. You answer how you will do statistical analyses and reasons why you may do so. And that is all done before you've collected the data. And this prompts the researcher to think about sample sizes and analyses and actually consider statistical power. And as I pointed out earlier, statistical power has been quite low. And this also protects you against researcher bias, accidentally doing those questionable research practices when you do analyze data. So because these pre-registrations are promoting the transparency of that process can improve the quality and reliability of your scientific research. Getting feedback and thinking about the experiment design rather than running headfirst and collecting data to try and produce something and bring that part of the research process and evaluating that earlier can save you time and mistakes and problems later on in your research project. So it can improve the quality and reliability and rigor and also the timing of your scientific research. For myself, and I think for many others, being open and having your data sets available and your code available increases the confidence in your own scientific research. By making sure I'm accountable to myself and others, I try and thinking about how others may want to try and reproduce and interpret my scientific data makes me certain about the quality that I am willing to promote my research to others, and so it increases the confidence in my own scientific research. And that's to say, it also increases reviewers' confidence when they're able to reproduce the data and see the data that is attached to your research paper and to your publications. And it can also improve the quality of their feedback. Maybe they can, once they're able to access the data, rather than asking you to do a specific statistical analysis, they can do the data analysis themselves, or they can easily understand how the data came about. And therefore, the quality of the feedback during peer review may be even better and high quality and can improve your research manuscript. And a simple reason, it may help you revisit previous experiments that you may be asked about potentially years past after you've done the experiment. For example, if someone asks you about a specific analysis that you did or a specific figure, or maybe you want to do a follow-up study which uses very similar code, if you've worked reproducibly and openly, you can much more easily revisit previous experiments. And for example, if you've uploaded your data to be open and publicly accessible, when you move between labs, for example, between graduate school and a postdoc or from a postdoc to faculty, it's much more easier to move the data with you and have the code with you if it's openly available and you've ensured that it's reproducible, rather than digging back through work that you did many years ago and trying to remember and retrace the steps that you took without any cues or any comments in code or any README files, for example. So those are some personal reasons to do open science. Some of you at this point may be concerned about engaging in open science for various reasons. For example, you may feel like it will take longer to engage in open science. It's something that you have to learn about and do. It's adding more steps to the research process. Well, I want to point out that actually open science seems to be a good thing for those incentive metrics as well. For example, open access publications appear to get relatively more citations than those that are not open access. You can think about this in terms of visibility. Being able to access a publication simply means that more researchers can get to it and it's more visible, and therefore researchers can then cite your work. Also, open datasets can be cited themselves, just like the example I provided earlier. Because I reanalyzed previously collected datasets, I cited those datasets in my paper. And that in turn provides more visibility for those datasets and the associated papers. Furthermore, open science promotes collaboration and community. Collaboration and community sort of protects against this individualistic approach to science and trying to further yourself. By being collaborative, you can also be more efficient, where you divide your labor between multiple groups and have it more efficiently produce the research that way. And I also want to mention that open science is increasingly considered in grants and job applications. Increasingly, job adverts are asking applicants to include a statement about how they incorporate open science principles into their research. And similarly, funding agencies are looking at open science as a way to ensure the rigor in the research that they're funding. And lastly, should we be beholden to the incentives? I'm referencing a Tal Yarkoni blog post, which is quite famous, where the title is "No, it's not the incentives, it's you," where he sort of laments the appeal to incentives for not doing rigorous and engaging in these kind of reproducible open science practices. My take on it involves something like if you're a junior scientist and an early career researcher, unfortunately, the odds of being an academic researcher are extremely slim. So why work towards that? Why be a gatekeeper of knowledge and instead enable others to make better inferences and have your science be more positively impactful in that way, and try and get scientists to have improved their pursuit for the truth and for real effects. So at this point, hopefully you are motivated to engage in open science or in reproducible science. How do you go about that? So firstly, open science is not, I don't believe, an all or nothing approach. Not being completely open in one sense doesn't invalidate the entire research process. But I think it was Bergman in a talk talked about open science as a buffet. And I like that analogy. I like the idea that open science is simply a set of research skills that will take time to develop. So if you're an early career researcher, you can devote time to training those skills. Here on the right-hand side, I've pulled a figure from Kafwala, Silverstein, and Syed, which is a great guide to easing into open science for early career researchers and their advisors. And in this figure, they sort of separated out the research process into 5 steps: conceptualization, design, analysis, reporting, dissemination. And some of the things that you can do, some of the open science practices that you can partake in those 5 stages. For example, starting a journal club to discuss these open science issues, thinking about your project workflow, or if you're an advisor, thinking about your lab's protocol to incorporate open science principles or reproducible principles into your workflow. At the design stage, I've mentioned pre-registrations earlier, also registered reports, which is the new format that thinks about in-principle acceptance at the pre-registration stage so that you're no longer biased or incentivized to produce a positive result. Planning how you're going to share your data once you collect the data, using reproducible codes, so for example, including comments or using GitHub to make sure your code is acceptable and has version control, for example. Transparently writing in the reporting stage, so making sure you don't obscure any details to hide potential pitfalls in your research or limitations in your research. And preprints, which I've mentioned. Preprints are where you can, is an easy open science practice to adopt. So for example, some journals actually allow you to post free copies, openly accessible copies of your manuscript on your personally hosted website. Not all journals, but some journals. And preprints are also another way around that, where you can post to, for example, SciArchive or bioRxiv or other repositories, a submitted version of the manuscript that hasn't been formatted, but has the general bulk of your ideas and is openly accessible. And this allows other researchers to access your research faster rather than waiting for the peer-reviewed published manuscript. They can access your ideas and actually cite those preprints to make better inferences in their own research. And data sharing on repositories like the Open Science Framework that I've mentioned. Again, data sets that are open can be cited themselves, and with more open data sets, they may be combined and combined and promote collaboration, as well as improve the quality of meta-analyses, for example, because they can actually get to the data rather than relying on the statistics reported in those manuscripts. So some easy open science practices to adopt include posting free copies of published articles, depositing preprints of manuscripts, publishing in open access venues as well. And some scientists are creating journals that are trying to cut down open access fees. For example, eLife. You can also publicly share your data and materials, as I mentioned, and attempt a pre-registration of your studies. Note that some of these are easy because some practices are a little bit harder to do. For example, you might need to learn a programming language like R to make your statistical analysis reproducible, or you might need to learn a new programming language so to make sure your experimental code is open source. So those are much more difficult, but the ones that I've listed here are more accessible and easier to adopt. I also really want to highlight reproducibility. So reproducibility was a grassroots journal club initiative. Here at a reproducibility journal club, you form an inclusive and supportive community around reproducible research practices and the open science movement. So the idea is that every week or so, you read and discuss relevant papers to stay informed about what the best research practices are. And as you discuss those issues and those papers, you share your experiences, and that can normalize any obstacles or barriers that you may have to engaging in the open science movement or engaging in research, especially if you're an early career researcher or a junior scientist. Once you've realized what those problems are, you may realize that they are common among the departments at your research institution, and this could encourage collaborations between labs. Perhaps others have expertise in a specific type of analysis that you can then bring them on to the research project to help expedite that research and help you out with your statistical analysis. And perhaps you find out that specific skills, like the ones I mentioned, R and GitHub, for example, perhaps many researchers at your Reproducibility Journal Club are interested in learning those, so you can organize skill workshops. Or perhaps you're motivated to learn Bayesian statistics, for example, so you can form learning groups around it. I'm not simply just making this up. I started the University of Chicago Reproducibility Journal Club a year ago, and all these things did happen. It's a very low cost and it promotes early career researchers, so I think it is a great initiative to be a part of. Full disclaimer, I am currently serving as a steering committee member of the Reproducibility Initiative, so I may be biased, but I truly believe that the Reproducibility Journal Club Initiative is a great way to get started and engage in the open science movement. That is all I have. Thank you for listening to this talk. It would be remiss of me not to thank my previous research mentors, Patrick Goodborn, Alex Holcomb, Ed O, and Ed Vogel. I hope you got something out of this talk.